Hi everyone, my name is Justin from the Small Artifacts Lab. I'm excited to present our work comparing vibro-tactile and skin stretch haptic feedback for conveying spatial information of virtual objects to blind VR users. This work is in collaboration with Zining Zhang, Ze Yuyan, Yuhang Zhao, and my advisor Huaishu Pen. So this is a Beat Saber. It's a very famous VR game that many of you might have played. And this is what the blind people would have experienced in this game. It is impossible for them to do anything because the spatial information of the cubes can't be delivered by the conventional head mount displays without the vision channel. So to make it possible for the blind users to use VR, it is key to help them to know where the things are and how they are moving. So otherwise, we are leaving them behind in this novel experience. So the good news is in the period, researchers have started to explore different ways. For example, using the assistive auditory system to provide spatial information. And also, the problem with the audio-only feedback is it can be easily interfered from the other sound source, such as ambient noises, background music, or talk from the other avatars share the same virtual space. So as a result, solely rely on the auditory feedback is often insufficient for conveying a clear and reliable spatial information. So beyond using the audio, researchers have tried to use haptics such as the vibro-tactile and skin stretch as an independent sensory channel. But they are mainly focused on the immersiveness, and instead of rendering this the spatial information here. And another, more importantly, is they are not targeting for the blind people, so missing the first-hand test result. So here we have a question, is for the blind VR users, which haptic mechanism can be better assist them in understanding spatial information? So to answer these questions, we designed a within-subject experiment to compare the vibro-tactile and skin stretch mechanism for the blind VR users. But before we conduct the experiment, we need to decide where to apply the haptic mechanism. Our decision is to apply both of them on the dorsal of the hand for three reasons. First is the high sensitivity. The second is the relatively large and flat area, and the third is its potential opportunity that both mechanisms can be engineered with the small form factors like this 2E. Next, we need to decide which type of the spatial information should be conveyed. In our study, we focus on two common types. The first is static information, and the second is the dynamic information. Then, to make our result comparable, we design an experiment device that is capable of rendering both haptic feedback on the back of the hand. So in the first task, we explored how blind users perceive static spatial information. We designed a coordinate system on the dorsal side of the hand to map the location of a virtual object. To evaluate participants' perception, we also measure the accuracy of their reports, the directional and the distance information. And here are the results for the both haptic mechanisms. And overall, we found the blind participants showed a higher accuracy with the skin stretch feedback compared to the vibro-tactile, and we also found the significant effect on the haptic mechanisms. And then in the task 2, we also investigated how the blind participant perceives the spatial information of a moving object. Similar to the task 1, we found the participant have a higher accuracy through the skin stretch mechanism in perceiving the moving object, and also the significant effect on the haptic mechanism. So due to the time constraint, for more detailed information, please refer to our paper. Yeah. So after we see these all periods result, can we make a conclusion with skin stretch is better than the vibro-tactile in conveying the spatial information? Actually, from the subjective feedback, the answer is not really. The opinion from the user's perspective are also divided. some participants mentioned the vibration feedback is clear and easy to recognize, and they are also very familiar with it. And other participants favor with the skin stretch mechanism because they feel more practical and also useful in perceiving the distant information. And also some participants mentioned the skin stretch is more useful in delivering moving object trajectory. So nevertheless, we recognize the benefits of both haptic mechanism for rendering the spatial information, and we know the higher accuracy doesn't mean it will have a better user experience. So the future research should be possible to combine them together to maximize their benefits. For example, using vibrotactile to deliver static information and apply skin stretch to deliver the dynamic information, and possible to make them compact and integrate with existing VR controllers. So thank you very much, and I'm happy to take questions.
Good afternoon, everyone. My name is Zining Zhang, and it's my pleasure to present Jet Unit, rendering diverse force feedback in virtual reality using water jets. This work was published at WASTE last year. Imagine you are a VR developer, and right now you're going to build a medical training stimulator. So first, you will need to stimulate light tap, a gentle tap, searching for the vein. And then you will need to stimulate a firm push as the injection goes in. So this scenario shows how a single task can demand distinct force feedback in quick succession. And in this case, we will need a compact wearable device that delivers both subtle discrete touches and strong continuous injections on tiny localized spots. And why this has become a challenge today. Currently, on-body haptic systems tend to specialize at one end of the spectrum. For example, Hydro Ring designed a flow system to deliver gentle tactile feedback on fingertips. And Impact Vest create a strong impact on torso to render strong sensations like a fire blast. And Force Jacket used a pneumatic system that deliver force feedback, diverse force feedback across a large area of the body. But it is still challenging to seamlessly bridge the gap between a featherlet type and a form poke, all within a self-contained form factor. So we propose Jet Unit, a water-based VR haptic system that uses water jets to produce diverse type of force feedback. And our key insight is simple yet powerful. Water is incompressible, so any applied force can be transferred almost entirely to the target. And by manipulating the intensity and frequency of the water jets, we can create a variety of haptic patterns, including light touch, strong poke, wave-like sensations, and different pausing theorems. And to validate Jet Unit, we ran a user study with 11 participants in a VR warrior mission. First, they received a touch-based VIN check. And then they got an injection to implant a magical chip into their body. Later on, they could activate the chip to power up their shield, and then they will trigger different waveform signals. Finally, they were sent to the battlefield, and they can defend themselves with the shield against the shot fired by a flower monster. Participants distinguish every pattern with 80 to 100% accuracy and praise the system for realism, usability, and enjoyment. Overall, Jet Unit has proven effective in delivering diverse haptic patterns with a wide spectrum of intensities and frequencies. We believe this opens exciting new possibilities for rich, immersive on-body VR experience. And thank you for your attention. I'm happy to take any questions.
Hi, folks. I'm Zoe from Computer Science PhD program. And then today I'm going to talk about two of the researchers in my recent line of research regarding sustainable making. And both of them were published at HCIL this time last month. All right, so in the past few decades, the computers have gone through a tremendous amount of evolution and democratization, and they become much smaller and are embedded in every corner of our lives. However, the fast evolution of these smart devices means that they have very short lifespan before they get replaced by newer generations. So in turn, this results in rapidly growing e-waste globally. And a small portion of these e-waste are transported cross-border to get to a centralized facility to get processed, but the majority of them are still going to the dumpster. Now, very lucky for us, another community emerged in parallel of personal computing, which is in a unique position to potentially tackle this issue, and I'm referring to maker community formed because of the democratization of fabrication tools. Now, this is a user map of Prusa, one of the leading open source 3D printer manufacturer. And here is another global map of where are the makerspaces and fab labs across the world. So as we can see, the maker community is co-located with where e-waste are generated, which is all everywhere around us. And additionally, the maker community is equipped with the knowledge and tools and experience to interface physical materials. And in fact, they have played important roles in multiple global crises. So the question is it possible that a maker can take part in the battle with global e-waste? Imagine that maker communities can be equipped with sustainable electronics production and recovery techniques so that these e-waste can be processed locally and form a local circular ecosystem geographically without the need to ship the waste to somewhere else to process and save the materials at the same time. So to understand the possibility of this approach, we conducted semi-structured interviews with 17 experienced makers who are stakeholders involved in physical making as different roles. And as a prior knowledge, to take maker community as a lens for sustainability exploration in electronics making. We aim to understand how makers today view the sustainability impact of their activities, how do they reduce their own waste, and motivations and challenges behind all these efforts. We notice that most of the time people are aware about the value of the waste streams. However, there are several reasons why they are still going to the dumpster. And the very first is lack of procedures and equipment. For example, one of our participants mentioned sawdust as a common waste stream in makerspaces created by machining, but there's no local infrastructure that supports recycling and reuse of them. And similar things happens to failed 3D printed parts, PCBs, and many other complex compound and assemblies. And the second reason people choose not to do anything more than just throwing things away is the cost. And this is not just monetary cost, but also time and effort to process these. For example, research lab would focus on research outcome rather than recovering material. And similar concerns is expressed by makers and managers. They have to prioritize the survival of their organization or business over sustainability. And the third reason is that people don't always have the knowledge or skill to do things. For example, one of our participants said, very simple example, not everybody knows how to desolder a motor from a product to reuse it, although it's very much likely to be functional. So now, makers are the ones who deal with physical materials on a daily basis, even they don't know how or they don't have the tools to deal with their own waste. And these challenges informs that if we want to contribute to the computing industry by processing e-waste locally, then we need to develop accessible and easy ways not only to produce, but also disassemble, decompose, repair, recycle, and remanufacturing of electronics. So out of all parts ubiquitously observed from electronic waste, PCB assembly is the core of computation and is also arguably the most complex compound in e-waste. And they have high recovery value, but also require sophisticated procedure and a huge energy and resource investment to recycle. So throughout my PhD, I've developed multiple research archetypes that spans all stages of PCB assembly's life cycles, including techniques that facilitate flexible and 3D circuit making, disassemble of electronic components for reuse, modification of PCB board that saves obsolete PCB substrate material, and also novel material combinations that makes PCBs totally different ways so that they are fully recyclable. I've talked about some of these in previous symposiums, and then today I'm going to focus on PCB renewal, which is the one that just got published at this KAI and received honorable mention. So if we take a look at a PCB assembly, they mainly consist of two parts. One is the electronic component, and the other is the board itself, and they're soldered together. And electronic components are usually coming in standard packages, and some of my previous research I just mentioned have explored ways to disassemble them and reuse. However, the board itself is considered permanently holding one circuit pattern, one schematic, which is not modifiable. So trash is their only destination after they're obsolete. But what if they are modifiable? So what if, like pencil drawing, we can edit circuits and change circuit on a PCB, just like we do it on paper? So PCBs are engraved or etched in an intaglio manner, meaning that copper are removed from substrates to form grooves that separate traces or signals. So to erase a trace, we should fill the grooves around that trace with conductive material, form a conductive local area so that this area can hold new trace in place. And this is the procedure or the principle we use in PCB renewal. And in practice, when we use this method to do it, we need a viable material to use as the conductive filler. We surveyed commonly available electrical bonding materials based on conductivity, curing condition, viscosity, and a lot of parameters based on that reflects the ease of handling. We found silver epoxy being the most suitable material for this task, let alone we're not using much of it. Now that we have a viable material, let's look at how we use it to renew PCB. For example, let's say we're changing the pin that controls the blinking LED from one of the pins to the other. Then this is a really small change that we need to make so that we don't need to flat erase the whole thing. We only have to erase part of it. So the first step would be we need to desolder all the components so that when we're curing the epoxy, they're not gonna reflow and mess up the renewal. And after that, we can apply the epoxy to where the trace needs to be erased, and then cure the epoxy on a hot plate or in a convection oven. And then re-engrave the new trace using a CNC milling machine or IR laser. And then we can solder all the components back, and now we have like a modified PCB that has a different pin that controls the LED. And to validate the performance of the renewed PCB, we conducted a series of experiments that shows the renewed PCB can perform common circuit functions on par with conventional ones. And you can refer to more details in our paper. I'll show a QR code at the end of the presentation. Now, intuitively, we can always flat erase a PCB and cut the new one, like using the flat erased one as a new substrate. And ideally, we don't have to do that. We only have to figure out the necessary parts to erase and re-engrave so that we can modify a circuit with minimal effort and resource. And this requires precise comparison between the two PCBs and output digital fabrication profiles. And to make that comparison easy to conduct, we built a software plugin that automatically does that. It's based on an open source EDA design tool. So a user can import the two circuit designs and compare them and then export the fabrication profiles. Here's the QR code to the GitHub link of the plugin. All right. And more importantly, with the digital profile, the software informs the users the resource savings regarding material usage, energy consumption, cost, and fabrication time. And this radar chart is showing the orange part is representing the conventional method, and the green is PCB renewal. So for each renewal case, even before it happens, users can look at the results and estimation of how much resource you can save, so they can make ad hoc decisions. And to demonstrate the potential sustainability impact of PCB renewal, we use one single piece of copper clad to prototype 3 artifacts sequentially across 4 iterations. Basically, all that you see came from one copper clad, and we calculate the resource saving across all iterations, and each individual cycle saves more than 90% of material in waste, meaning that we're trading milligrams of silver epoxy with FR4, which is the common material made for making PCB, of 30 to 60 times of the weight. So in general, PCB renewal enables erasure of obsolete PCBs to make new ones and saves material and cut e-waste and resource consumption of making circuits. And in the future, I'll explore more locally deployable techniques and infrastructures that collectively form circular material flow and hopefully mitigate global e-waste and sustainability issues beyond. I'd like to thank all my collaborators who contributed a ton to the projects they presented today. Thanks for listening.
So, hello, my name is Clayton, as you just heard, and this is HCIL. And we are presenting right now on behalf of Tech on the Block, and we're also doing with CREED, which is Community Research, Equity, and Design Collective. And we're presenting challenges and opportunities in structuring and facilitating an XR-focused co-design program for Black and Brown middle school boys. As we march forwards in time and technology gets more and more advanced, tech literacy has never been more important. And this is especially true in today's time. Tech literacy could be at its most valuable. However, we've noticed that marginalized groups, and like historically marginalized groups especially, might have limited access to these emerging technologies. So to address this concern, what we decided to do was run a 2-week sort of summer program targeted at rising 5th grade to 8th graders, predominantly in marginalized groups. And it was for the purpose of introducing them to XR, which is, like VR, AR, that sort of deal. And after we did that, we decided to do this research, which is to answer the question, how can we create a welcoming and engaging informal learning environment for Black and Brown? You've heard it. So important to note is that this research question focuses on the program. So our methods for this research was to use three auto-ethnographic focus groups. These groups were 3 of our core research team members, which are UMD professors and a doctoral student. And then we also had a group with 3 of our near-peer mentors, which was facilitated by 2 of the core research team members. And then we also had another focus group where it was one core research team member, and then 1 near-peer mentor. So it was a one-on-one. Okay, so what we decided to use was a thematic analysis, and we were really seeking to answer the question of how we could make the program better for a next go-around in the summer.
Through these processes, we observed that our team had the shared desire to balance, our shared desire to provide the children with self-directed learning opportunities and enforcing constraints that supported their safety and creative project development. So we divided our time at the camp into 2 main activities that we wanted to focus on, the first being VR headset use during free choice time. So we wanted the children to be able to choose which activities they wanted to do on their own, but we grew concerned when we noticed the same set of children sort of repeatedly refusing to share the VR devices. To fix this, we imposed and strictly monitored time limits on the VR devices. But we also asked that children sort of self-direct themselves in the content they were viewing with the VR, but we found this difficult to enforce due to our inability to monitor their activity in real time. The second main activity we wanted to focus on was final project development, which is a little bit more of a structured environment. We found it difficult we found difficulties in fostering engagement and motivation in the children in this more structured environment, but when we let them pursue their own interests, they had trouble getting started and defining an interest that was okay for everyone in the group. They were doing a lot of group work in this time. So to give an example, children in a 5-child group, children 1 and 2 may have proposed one idea, children 3 and 4 may have pushed another, and child 5 may have been completely at a loss for how to even get started. They face difficulty in reconciling these different perspectives and navigating the social dynamics at play. In addition to all that, many of the children were also focused on developing novel ideas that pushed the limits of their design capabilities, especially when they were using tools, design tools they weren't completely familiar with. Though these tools did have a certain learning curve for them, they ended up being part of the solution in the end. The constraints of these tools helped to ground the group's ideas, which ended up being very blue sky, sort of infeasible ideas sometimes. So they helped sort of bridge their ideas with realism and encouraged a more well thought out and planned design. Additionally, we found that adult facilitation of compromise between children went a long way in helping them get started and create meaningful breakthroughs in communication. We come away from this research with 2 main implications. The first being facilitation over instruction. This suggests that mentors should focus on advising the children in a path that they designed themselves rather than creating a set, rigid structure for them. The second constraint is that, or the second implication is that constraints can both limit and enable child co-design. This implies that when using tools such as Bezier and Figma, which may be unfamiliar to the children, these design tools, they can also, though they're limiting in their unfamiliarity, they can also enable the children by encouraging them to think deeper about their project and how to really bring it to life. Though this research doesn't have any concrete results yet, we believe it does point out certain issues in this field that definitely need more looking at. Thank you for your time.
Hi, my name is Jincy.
My name is Ellie.
And we are students in the Undergraduate Research Opportunity Program. And today we're going to be discussing the research we've done in collaboration with Beth Bonsignor and Alana Blinder, reflecting on adult questioning and prompting strategies in co-design with children. So this past semester, we had the opportunity to work with the UMD Kids team, which is a co-design group where adults and children collaborate as equal partners to design technology for kids. And throughout the semester, we found ourselves wondering, are we asking too many questions? Are we being too quiet? And overall, are we even being helpful? These reflections led us to study the balance between offering support and avoiding dominating the collaboration. So to explore this, we strive to answer what questioning and prompting strategies can better support adult-child collaboration and shared creativity during co-design. So we collected data from 2 stakeholder groups, UMD Kids Team stakeholder groups, adult design partners, and child design partners. And so first we wanted to gauge our effectiveness as adult design partners. So we revisited audio recordings and transcripts from our previous sessions and wrote short reflections on the questioning and prompting strategies that we used. Then we conducted a kids team session focused on understanding children's perception of a good and bad adult design partner. So we started off with the question of the day, which is, imagine you're at school and your friend is stuck on something. How would you help them get started? Then we initiated a line judging activity where we shared 2 fictional design scenarios with the kids, after which the children indicated their desire to work with each fictional design partner. Afterwards, the kids designed the best and worst design partner archetypes by describing what they might do, say, feel, think, and even what they look like. And lastly, the kids engaged in a reflection activity by writing or video and audio recording letters of advice to future adult design partners.
So over the next month, we plan to complete our analysis of the data. We are currently coding our written reflections, co-design transcripts, and artifacts using thematic analysis, as well as developing a codebook to apply across the data in a second round of coding. Our data consists of 8 kids and 5 adult undergraduate students. So far, main themes include disposition and qualities, pacing of questions, and quantity/quality of questions asked. So far, we have mainly found that children emphasized how adults made them feel, qualities like kindness, patience, and not being too bossy, and asking enough but not too many questions. Adults similarly focused on how the delivery of questions and prompts, such as interrupting kids, not giving them enough space to answer, could affect children's experience and overall design process. Both adults and kids emphasized listening, respect, and balanced communication as essential to being good design partners. These preliminary findings suggest that good, effective co-design partnerships rely less on specific knowledge and more on general emotional intelligence. Understanding kids' perspectives on the ideal co-design partner benefits the kid designers, undergrads who are new to the design process, and overall advances the field of research. Undergrads will have a clear set of principles to follow that were created by kids well-versed in the design process and that had worked with many different adult designers in the past, thus resulting in effective collaboration between adult and kid designers. Having these strong adult-child design partnerships will improve the experience of designing in kids' team and the quality of the design outcomes in general. Our research was a good first step in creating the ideal adult-child design interactions. Our findings can potentially help advance the field of child-computer interaction, as we expect children to be more inclined to work with adults. Adults will feel more confident and therefore give appropriate guidance to children, and therefore making the process as fun and as effective as it can be. Thank you.